back to you at the end of class. The grades were not great on the exam, and it's because of a couple of things. A number of you are still struggling with things like the difference between type 1 and type 2 error and how to interpret things like p-value. Another issue was that when I would ask you to tell me about the relationship between one thing and another thing, some of you tended to define what the one thing was and not say anything about the other thing, or if you did, you tended to define what one thing were, but you didn't tell me how they were related. So for example, how are type 1 and type 2 error rates related to one another? As type 1 error rate goes up, what happens to type 2 error? It tends to go down. And so when I asked you for a relationship, you didn't tell me what the relationship between them was, even though that was in the question. Like I said, when you get them back, you'll see that if you made a mistake in the calculations, for example, of the mean or of the chi-square test or anything like that, and you made an arithmetic mistake, I would basically take that and plug it into the rest of the formulas and basically test you on the process rather than test you on an exact right values. If you didn't show me your work, it was considerably more difficult to do that. Because if you showed me your work, like I asked you to, I could actually identify where exactly you went wrong, and then basically, once again, give you credit for knowing how the process works versus not knowing how the process works. If all I had was a bunch of numbers in the blanks, all I had to go on was the numbers that you provided me with, and I would plug those in, and in a couple of cases, it was just wrong from there on out, and I had no idea of kind of assessing where it was that you were going wrong in the process because there wasn't any work shown. So, today is when 5-week grades are due. I have your exams graded. I'm going to go through your problem sets as soon as I get out of class today. So by the end of the day today, on the Moodle side, I will have the coin flipping data problem set, the coin flipping exercise grades will be in there, the initial problem set you did will be in there, and your exam grade will be in there. So at that point, you'll know what all the graded assignments are that are in there, and you'll have some idea of what your score is, because the exam is 100 points. The first problem set was 50 points, and the coin flipping was 25 points. So essentially there are 175 points in the class so far. So whatever your total grade is, let's say that you have 100 out of 175 points, that equals your percentage grade times 100. So you'll be able to get an idea of where you stand, and that's how I'll calculate your grade for your 5-week grade report. So that's that. All right. We were working through analysis of variance last time. For those of you who were gone, we were working through the P example, the example where we have a control watering plants with 2% glucose, 2% fructose, 1% glucose, 1% fructose, and 2% sucrose. These are what the data look like. And I was going through how one goes about calculating sum squares within, sum squares among. You can add those two things to get sum squares total. You have the degrees of freedom associated with each of these things. The degrees of freedom is the total sample size minus the number of treatments that you have, and the degrees of freedom for sum squares among is the number of treatments minus 1. These two things added together give you the total degrees of freedom for total.
What is the number of treatments?
In this case, it's 1, 2, 3, 4, 5. We have a control, glucose, fructose, glucose, and fructose, and sucrose. 1, 2, 3, 4, 5.
And
N is the total sample size. So there are 10 observations in each of these, so our total sample size is 50. So in this case, it would be 50 minus 5, so that would be 45. We have 5 different treatments. This would be 4, and 49 is the total degrees of freedom. The total degrees of freedom is always the total number of observations minus 1. So if we have 50 observations minus 1, that would be 49, and this plus that should always equal this. So once again, with degrees of freedom, you should always be able to ascertain whether or not your degrees of freedom are right, because you know what the total degrees of freedom are, and the sum squares within and sum squares among should always equal the total degrees of freedom. I do not know why dry erase work does not want to dry erase. So while we were going through this, I had prepared a spreadsheet that evidently had some wrong numbers in it. I've corrected that spreadsheet, which is why there's a new version of the PowerPoint. The sum squares among is the mean of each of the different treatments minus the grand mean squared, but then you multiply it times the sample size. So you always weight the sums of squares among by whatever the sample size is. In this case, each sample size is essentially 10 of a given, the sample size of a given treatment is equal to 10. So you would multiply 10 times the difference between the mean and the grand mean and square that. And so as we were going through, as I was going through this whole thing, this line is incorrect. So what I have in this table, this is basically an Excel spreadsheet that I made up some time ago. If you add all of these up, this is the sum of the x values. Divide that by 10, you get the mean. The sum of these x values divided by 10 gives you the mean. The sum of these x values divided by 10 gives you the mean, et cetera, et cetera. In this case, because these are all the same sample size, you can actually calculate the grand mean by just adding these things up and dividing by 5, because you have 5 different treatments. The more appropriate way to do it would be to, over in this cell, just add this whole thing up and divide by 50, and that will give you the grand mean. So this is the grand mean, which is all of these things added up divided by 50. The sample sizes are all the same, so your grand sample size is 50. And then sums of squares within basically takes 70.1, subtracts it from 75, squares it, does that across all of these, and then sums them up. So this is 75 minus 70.1 squared plus 67 minus 70.1 squared plus 70 minus 70.1 squared, et cetera, et cetera. Added up, same thing here, it's 57 minus 59.3 squared plus 58 minus 59.3 squared plus 60 minus 59.3 squared, all added up. That's what each of these sums of squares within is. And when you sum those all up, this is the sums of squares within. Sums of squares among, you basically take this mean minus the grand mean, multiply it times 10. Oh, sorry, this mean times the grand mean, this mean minus the grand mean squared times sample size. So sum squares among is the sample size times the mean minus the grand mean squared, summed across all of the sample means. So 70.1 minus 61.94 squared multiplied times 10 is what this should be. 59.3 minus 61.94 squared times 10 is what this should be. Athos.
Can you write down the SS with name formula as well? and the total, please?
Yes, I can. Sum squares within is the individual values minus their sample mean. If I refers to the number of observations in a sample, and J is the number of treatments in this case, Xij is the ith observation within the jth treatment, is kind of the mathy way of saying this. So the most rigid way of writing this would be to take the ith observation from the jth treatment, subtract that from the mean of treatment J, square that, sum that across all observations from I to n sub I, sorry, n sub j rather, the sample size of the jth treatment, and then summing that from the first treatment to the yeah. So this basically says take each value, subtract it from the mean within a treatment, then sum that across all of the values within that treatment, and sum that across all of the treatments. And so that's what we're doing here. We're basically taking the ith observation in the jth treatment, so the first observation in treatment 1, subtracting from that treatment 1's mean, squaring it, adding it to the second observation in treatment 1, minus the mean of treatment 1, and squaring it.
And sum everything divided by the n numbers?
And then sum all of that, and you don't divide by anything in this case, because we're just doing the sums of squares, the sums of the squared deviations from the mean.
Okay, so how can be that possible with number 10? Because 75 minus 70 is like almost 5, and 5 squared is 25. And we got 10. We need to divide it.
So this is, what are you saying, this?
Yes. Oh, no. Yeah.
This is sum squares within, it's this plus that plus,
From number, I thought you were pointing for the n, number 10.
oh, no, this is the sample size.
Okay.
10, 10, 10, 10, 10, they're all the same, that's sample
Yeah,
size.
yeah.
So 142, all of these things, if you continue doing this down the whole thing, add all of those values up, it should sum to 142.9. Do the same thing for this thing, except not minus 70.1, minus 59.3 squared. For this one, it would be minus 58.2 squared. All down, they should sum to these values, and then you sum across all of the treatments. So do this for all of the values within a mean, then sum across all those values within the mean, and then sum across all of the treatments that you have. In a similar way, I'm sure the person who teaches after me hates the fact that I draw on the screen. In this case, sum squares among is the sample size, which in this case is 10, times 70.1 minus 61.94, which is the grand mean over here, squared. So 70 minus 61, that's about 9. And 9 squared is 81. No, that can't be right.
It's 8.
Oh, it's gonna be closer to 8, isn't it? Yeah. So 8 is gonna be around 64 approximately, times 10, that's close enough, because we're just guesstimating what their numbers here. So 59.3 minus 61.94 squared times 10 is this value. Each of those things is done for each mean J minus the grand mean for each sample. Take the sample mean minus the grand mean, multiply it times the sample size of that mean, sum that across all treatments from treatment 1 to the maximum number of treatments that you have. And then sum squares total is just sum squares among plus sum squares within. Or if you wanted to calculate it the long way, it's the difference between each of the individual values minus the grand mean squared, summed once again across all values within a treatment, and then summed across all treatments. So you can figure this out either way. So to figure out the sums of squares total, it would be this value minus 61.94 squared, this value minus 61.94 squared, this value minus this value squared, this value minus this value squared, done for the entire data set. It's how each individual data point varies from the grand mean across all treatments. The reason that this should make sense is, so conceptualize it this way. There are different sources of variation. There is some variation among your data due to random sampling error within the treatments that you're dealing with. What kind of variation is this?
That's the within variation.
This is sums of squares within. How much variation is there between each of the data points and the sample mean? Each data point, sample mean, each data point, sample mean. Atlas? Question? Okay. So that's one source of variation. Another source of variation is variation in your data due to the effect of the treatment. What is this? Some squares within, some squares among, some squares total. Some squares among. It's basically how far does this mean lie from the grand mean? How far does this mean lie from the grand mean? How far does this mean lie from the grand mean? How far does this mean lie from the grand mean? How far does this mean lie from the grand mean? Those are two components of variation. So there's all of the variation in the data set, which is treating, let's assume for a minute that the treatment has no effect. If the treatment has no effect, these treatment designators have no effect. And as a result, what we have is one big population that we've drawn each of these samples from. We've essentially drawn a set of controls from a population, another set of observations from that same population, another set of observations from that same population, a fourth set and a fifth set of observations from that same population. But because the means are not different, those different subsets of the data are drawn from the same underlying population. That population now has a sample size of 50 drawn from it, and what is the average value of that sample size of 50? Assuming that treatment doesn't matter, we've drawn 50 observations from a single population. What's the average value for that sample? It's the grand mean. And so If we don't have any sort of treatment structure that's leading to variation, the overall variation in the data set is just how do each of these values differ from the grand mean. And so the total sums of squares is basically how much variation is there in the data. If treatment doesn't explain anything.
This is the amount, right?
No, this is total.
So,
This is amount. This is sum squares within. This is sum squares among. If the treatment doesn't have any effect, you just have one big population that you've drawn your samples from. The mean of that sample is the total sample size of the data set that you have, and that's the grand mean. And the variation within that population, within that sample, is just the individual values minus the grand mean squared, summed across all treatments and all observations. And so think about it this way. If there is no effect of treatment, sums of squares total will equal sums of squares within. So if there is no effect of treatment, there's going to be no variation between the means of the samples and the grand mean, because there's no effect of treatment. All of these treatments will be centered around the grand mean. If that's the case, then all of the variation that is in your sample size is going to all be due to variation within samples. If that's the case, then no variation is explained by treatment. All of it is just random variation within sample means, and so there is no effect of treatment, essentially. The more the sample means differ from one another, sum squares among gets big. As more and more variation of the total variation is accounted for by variation among means, less and less of that variation is accounted for by within sample variation, and you begin to see the differences between the means that you're looking for. And so one way of thinking about sum squares total is what would the total variation be if there was no effect of these different treatments. Now in this case, there is an effect of these different treatments. The control experienced more growth rate than everybody else. The sucrose group exhibited less growth than the control, but more growth than these others, and these others are essentially not different from one another. And we see that when we go and run the numbers, if the numbers would just appear. Oh, yeah. So we see that when we basically quantify sums of squares within, adds up to 245, sums of squares among adds up to 1,077. Down here in an analysis of variance table, we basically have the source of variation. Is it variation among means or is it variation within means? There are 4 degrees of freedom because we have 5 treatments. We have 45 degrees of freedom because some of those degrees of freedom got used up as we estimated means. The total is 49. Sums of squares divided by the degrees of freedom is the mean squared. Sums of squares divided by the degrees of freedom is the mean squared. The F statistic is the mean squared divided by the mean squared among divided by mean squared within, and then that's the thing that we test. And so we plug this in with an F of alpha of 0.05, degrees of freedom in the numerator of 4, and degrees of freedom in the denominator equals 45, and we get some table value for for an F statistic, and then we compare our F statistic against that F statistic. So what we can do, so when I say numerator and denominator, I basically mean numerator and denominator of the F statistics. So F is mean squared among divided by mean squared within. So what are the degrees of freedom associated with the numerator? It's the number of treatments minus 1, and the degrees of freedom of the denominator is the grand total minus the number of treatments, 4 and 45. So we can go to, for example, Daniel Silver's website. And we can ask his website, what is the critical value of F that we would need to be larger than in order to reject the null hypothesis that there are no differences among the means? Go to analysis of variance, F calculator for an analysis of variance, and what it asks you for, oh, no, back. Go to the critical F calculator. Degrees of freedom for the numerator is 4. Degrees of freedom for the denominator is 45. We're going to calculate this using an alpha value of 0.05. And what it should do is it should give us the F statistic. So our tabled F is 2.5, 787. Our observed F is 40, whatever it was. 49.37. This F statistic, F value, is way bigger than this F value, which is why when we go and calculate, so our F value that we calculated was 49.37. If we go back into another area of Daniel Silver's website, and instead of getting the critical value of F, we decide that we're going to actually get the p-value. Give it the number of degrees of freedom among, which is 4, number of degrees of freedom within, which is 45, and our F value that we observed was 49.37. The p-value that we get is essentially 0. So when we calculate this, we find that p equals 0, which is way, way, way less than p to the 0.05. We would conclude that at least one of these things is different from the others. When we do this in R, we actually get a p-value when we run it in R. And the p-value that I got when I ran it in R is 2.6 times 10 to the minus 16, which is just R's way of saying it's so low it's practically equal to 0. This is the lowest p-value that R ever produces. It won't ever tell you that it's 0. It's just going to tell you that it's some diminishingly small number. And so it's like 2.6 times 10 to the minus 16th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is the p-value that R gives you when things are just so different it's not even funny to talk about. And so this is way lower than a type one error rate of 0.05. And so if you say that two or more of these means are different, your chances of saying that and being wrong is diminishingly small.
So they are the same,
What are the same?
the means.
No, they are not the same. This means they are not the same. So this is an issue that's on the exam. What is alpha? Anybody? Well, what does it define it for me?
Type one error rate.
Okay, so type one error rate, I'm never gonna ask you what the type one error rate is. I'm never gonna ask you alpha in this way. What is the type one error rate? Describe it for me.
So you conclude that two means are different, they're not.
It's the rate at which you conclude two means are different when they are not. So this is a mistake. You said two means were different when they're not. What do we usually set alpha at?
0.05.
Okay, so we're basically set that at 0.05 because we don't want to make this error. More than 5% of the time. Right? Okay. So, now what is P? Define it for me, someone.
It's the probability of one error
Based on what?
based on whatever test you just done.
So, when we want to make a decision about whether two means are different from one another, what we do is we compare P to alpha. If P is 0.06, what does that mean for our data set? Our data set has
6% chance to be something.
a 6% type 1 error rate. But we said that we don't want a type 1 error rate greater than 5%. P of 0.06 is larger than P of 0.05, so we would conclude that things are not different. Why? Because if we say they're different, we have a 6% chance of saying they're different when they actually are not. It's an arbitrary boundary, but it's a boundary that we have crossed out of the realm of significance to the realm of not significance, because we don't want to make a type 1 error rate any more than 5% of the time. If we have a P of 0.049, is this more or less than 0.05? It's less than 0.05, what would we conclude?
That whatever we're looking at are different.
We would conclude in this case that means are different. Do we still have the possibility of making a type 1 error if we conclude this?
Yes.
What's the rate at which we can expect to make that type 1 error? 4.9%, which is less than 5%, which is why we then say things are different. So we observed for this data set a P p-value of this, would you say that these are different or not? Based on this p-value, this was the p-value for this data set. Is it less than 0.05? When your p-value is less than 0.05, what do you conclude? Something in there is different. Not only is something in there different, something in there is way different, because your probability of saying two things are different and being wrong is astronomically low. Astronomically low. You're not going to make a type 1 error rate if you say at least two of these means are different.
So I can create assumptions in this data set based on type 1 error.
I don't know what you mean by assumptions.
I can play with it. I can say they're different, they're super different.
All you can say is that at least two of these means are different from one another. It doesn't tell you which means are different from which ones. We have ways of figuring that out, which we'll talk about here in a little while. But it basically tells you that in this data set, at least two of these means are different. We already know, because we've looked at the data, which means are different from one another, but if you didn't graph the data already, you would basically just be able to say, somewhere in here, two of the 10 different combinations. So remember, we have 10 separate combinations. We could compare the means of sample 1 to sample 2, sample 1 to sample 3, sample 1 to sample 4, sample 1 to sample 5, 2 to 3, 2 to 4, 2 to 5, 3 to 4, 3 to 5, 4 to 5. That's 10 different combinations. At least one of those shows a difference. That's all that tells you. It could be that more than one of those shows a difference, but it tells you that at least one of those comparisons is different. These equations here are the equations that do all of these things. So, once again, treatment 1, I've switched the i's and the j's actually when I wrote it on the board. Treatment 1, the mean of treatment 1, the sums of squares within is the values minus the mean of treatment 1 squared, all summed up. All those get summed up to make the sums of squares within. Sum of squares among is n times the mean minus the grand mean, and then the sums of squares of, well, it doesn't have sums of squares total up here, because sum of squares among and sum of squares within is just the sum of squares total. But I showed you what that is. It's just the square deviations from the grand mean rather than sample means. Each of these values can then go into an ANOVA table, which shows you the degrees of freedom, the number of treatments minus 1, the total sample size minus the number of treatments, total sample size minus 1. Sum squares among is from the previous one, sum squares within is on the previous page. Mean squared is sum squares among divided by degrees of freedom, sum squares within divided by the degrees of freedom, and F is mean squared among divided by mean squared within. Which is what we just did with an actual data set. What is S squared?
Variance.
It's variance. It is sample variance. Who can tell me what the equation for sample variance is?
X minus the mean squared.
It's the sum of the squared deviations from the mean divided by
N minus
n minus 1. What is the mean squared?
Ask that again?
What is mean squared? Any of these mean squared?
Sum of the squares among divided by sum of the squares divided by the,
Mean squared. Go ahead.
I guess sum of the squares among divided by degree of freedom treatments minus 1.
Divided by the degrees of freedom. Yep. sum of the squared deviations from the mean divided by the degrees of freedom. When we calculate sample variance, what are we actually calculating?
Variance in the.
We're actually calculating variance within. It's the sum of the squared deviations from the mean divided by the number of degrees of freedom. In this case, what makes it the sum of the squared, what makes it the variance within is the fact that the mean that you're comparing these values to is the mean of the sample, and you're comparing the individual values to that mean. So when we write S squared, this is simply mean squared within for one sample. We would add these up across all of the different treatments. To get the mean squared within value that is up here. That is right here. When we calculate the sum of the squared deviations of the means from the grand mean and divide that by a minus 1, which is the degrees of freedom for the number of treatments, what are we once again calculating? We're calculating a variance estimate. It's the sum of the squared deviations from the grand mean divided by the degrees of freedom associated with that. I made the point to you when we talked about variance at the beginning of the semester that this was a crucially important idea for you to know. The reason this is a crucially important idea for you to know is because it's the basis of an analysis of variance. What separates the variance among and the variance within is the things that you're comparing. In variance within, you're comparing individual values to the sample mean. For variance among, you're comparing sample means to grand mean. That's the only difference. The calculation, though, is still the same. It's the sum of the squared deviations from the mean divided by the number of degrees of freedom associated with that comparison. It's all just calculating variances. If you know how to calculate a variance, you know how to work an analysis of variance. I also made the point at the beginning of analysis of variance It's called the analysis of variance because it's not an analysis of means, it's an analysis of variance. One type of variance, variance within samples, compared to another type of variance, variance among samples. The ratio, the F ratio, is the variance among samples divided by the variance within samples. This is essentially the mean squared among divided by the mean squared within, because the mean squared among is simply the sums of the squared deviations of the mean among means divided by the degrees of freedom associated with that, and the sum squared within divided by those degrees of freedom, and that basically is a variance estimate. That's what's called analysis of variance, not analysis of means. If you can calculate a variance, you can calculate a mean, which is why knowing what sums of squares, that SS stands for, it's the sum of the squared deviations from the mean. The question is, what's deviating from the mean and which mean are you talking about? deviation of individual values from the sample mean? That's sum squares within. Is it the individual means from the grand mean? That's sum squares among. If it's the individual values from the grand mean, that's sum squares total. But it's all just sums of the squared deviations from some mean. Questions about this? This is fundamental. Because you know what? When you do a regression, it's all the same equations. And a regression is actually just an analysis of variance in a different form. It works the same way. If you know how to do an analysis of variance, guess what? You know how to do a regression. How you do some of the parameter estimates is slightly different, but in terms of evaluating whether a regression has a slope different from a slope of 0, it's done within a ANOVA table. It's magical in that way. When you get to analysis of covariance, same thing is going to happen. Basically, everything else we do in this class, except when we're working with non-parametric techniques, everything we do in this class is going to go back to this table. If you don't understand this table, you're sunk. In the same way, if you didn't understand what variance is talking about, you're sunk. In the same way that if you don't know what type 1 error rate is and how that relates to p-value, you're sunk. These are fundamental base concepts that you need to have in your belt because we're going to be using them over and over again. Any questions about this?
Help me out with the degrees of freedom in the top formula in the box.
This
I mean, that's the generic formula.
This is just sample variance, which is one type of variance. This is the variance.
That's the general form of that.
Variance within a single sample.
Well, that's my question.
Yes, that's what this is.
With n minus 1 as degrees of freedom, that's kind of the general form of the variance.
It's a general form of the variance.
But once we start talking about within, that's not the denominator, right? The denominator is.
Oh yeah, sure it is. When we do this, it's the sums of the squares. This is the sums of the squares for treatment 1. This is this numerator.
Right.
So this is not the general equation. If you want a general equation, this is the general equation.
Okay.
Because this is the sums of the squared deviations from the mean, the sample mean, given the number of degrees of freedom associated with sample variance. So sum of squared deviations for the mean divided by degrees of freedom. This works for anything that you might deal with. It's just that what are you comparing and what are the degrees of freedom for that comparison? If you're comparing means to the grand mean, the degrees of freedom has nothing to do with n because the number of means that you have is about the number of treatments that you have, so the degrees of freedom changes.
Okay.
But in all cases, this is still a sum of the squared deviations divided by the degrees of freedom.
Right.
It's just the degrees of freedom that you use varies on what kind of comparison you're making.
And when we're talking about a variance within, I thought the degrees of freedom was capital N minus A.
It is because this is within a single sample. The question that you're asking about is sums of squares within across multiple samples. And across multiple samples, you don't just have the sample size of 1. You have the sample size of 1 in treatment 1. You have the sample size of treatment 1. You have the sample size of treatment 2. You have the sample size of treatment 3. You have the sample size of treatment 4. For our example here, we had 5 treatments. 1, 2, 3, 4, 5. They each had an N of 10. What's the degrees of freedom for a within sample variance?
Is the sum of a minus a.
Well, no, for a single sample.
N minus 1.
N minus 1. What's N minus 1 in this case?
40.
9,
Yeah.
9, 9, 9, and 9, right? What's 9 times 5? 45. You had 50 samples total. You had 5 treatments.
So when you scale up from single sample to
It's
multiple
just
treatments.
this summed across all the treatments that you have. It's just within sample variance. That's actually the point that I'm trying to get across to you. It's just within sample variance. Only now, instead of having a single sample, you have 5 samples. Does that make sense? The math should always work out. If it doesn't, you're thinking about it in the wrong way, or you've calculated something wrong somewhere along the way. Yep. So another way of saying the grand number of, the total number of your sample size across all treatments minus